Eliminating parameters and converting. What we're going to be doing is taking the parametric equations and blending them together so that we can have an xy equation. Taking a set of parametric equations and creating the rectangular equation, that would be the xy equation, is generally a simple idea. Now, in some problems, yes, it is more complicated, but in most cases, what you can do is use one equation to solve for t in terms of x. Then you can take that equation for t in terms of x and substitute it into the other equation that involves y. Okay, so if we solve here for t, we'll get an expression that involves x. We can then substitute that in for the t value here and get an equation that would be y in terms of x. All right, to see what that looks like, let's go ahead and solve for t here. We'll go ahead and subtract the 1 over to the x, which is going to give you negative 2t. Then you divide by negative 2. Divide both sides by negative 2. Let me fix those up so they look like negatives. A little messy there. All right, divide by negative 2, and t is going to be equal to x minus 1 divided by negative 2. All right, so then that expression, this right here, is going to get substituted into the other equation because it represents t. So then y is going to be equal to 2 minus this right here. All right, and one thing that you're going to notice here is that you got a negative out front. So typically we'll distribute that in, and we are going to distribute it in, but instead of distributing it to the numerator, you can actually distribute it to the denominator, which will cancel out the negative that we have there. Okay, so we can change this into a plus. We'll keep the parentheses right now, x minus 1 over 2. For the most part, we can probably figure out that this is a linear equation. We do have x to the first power, and x is sitting in a numerator position. Okay, so if I move things around a little bit, I can probably make it look like slope-intercept form. Right here, that would be your mx part. Okay, so we can get y equals, let's just call it x over 2. It is the same thing as 1/2 times x, so you could think of that as a rise of 1 and then a run of 2. Okay, and then this part right here, that 2 is going to go along with the negative 1 as well. So you can get a negative 1/2. If you subtract 1/2 from 2, that would give you positive 1.5. So it looks like we would have y-intercept at 1.5 and a slope of 1/2. Let's go ahead and graph that over here. Let's go ahead and graph that, and then afterwards what I'll do is type these into the calculator to see the calculator graph it and create that line. All right, so we do have a y-intercept of 1.5, which is not really convenient, but I think this is going to work out all right. So it'd be right there. The slope is going to be a 1/2. Okay, so from that point, you could go up 1 unit, which would put you at 2.5, and then go over 2, which will get you here. And if you think about connecting those together, you would end up at that point right there. Okay, so maybe instead of using all the half points, what I could do is just then skip over to here, okay, because that would be down 1 and back 2. Right, and then we can do the same thing from here, so go down 1, back 2, and that will actually give you an intercept at negative 3, which looks pretty good. All right, so go ahead and connect these together. Let's see, we'll have a dot right there, so I might as well use it. All right, and this is what I believe the xy equation is going to look like for these parametric equations. All right, so let's go ahead and take a look at this in the calculator just to see if we end up with that actual graph. You do want to make sure your calculator is set to parametric. Okay, so I go to the mode, which I actually do have it set. It's in parametrics. Go to y equals. The x equation I'll type in. So we're going to do 1 minus 2t. Okay, and then for the y equation, we got 2 minus t. All right, so the range of values we have for t is going to be negative infinity to infinity, which means it's pretty much any value you want. Okay, now when we set this up though, so you can't actually type in negative infinity, infinity. What we'll do instead is just choose a decent negative time and a positive time. So in this case, I went with negative 10 and positive 10. If it doesn't graph the whole picture going across the screen, what that would mean is that our that our range for the time is not quite big enough for this. But you don't want to go too big either, because if you do that, it takes a while for these to actually graph. All right, so for the rest of it, the mins and maxes for x's and y's, what we'll do is go ahead and use what I already have set up here. Okay, so the x minimum is going to be at -4, the maximum is going to be at 3. For the y values, -4 up to +4. Okay, and then when we graph this, we should see an intercept here at -3 and an intercept at 1.5. All right, and it does. And you know what, I guess what my window is probably not set up correct. Let me backtrack and figure out, how did that work? Is it because of my step? Oh, it's my scale here. We'll change this to 1. Not sure how that got messed up there. All right, so that'll be a better picture of it that we want to see. All right, so then what we see here, of course, is the intercept at -3. You also have the 1.5, which is there. So this is the equation that would match these parametrics that we have. All right, for example 2, we're basically going to do the same thing here. We're going to start by taking this equation and solving for t in terms of x. And to do that, I'm going to use cool trick number 4, which is going to allow me to switch these two with each other. Okay, so I can write that the square root of t is equal to 1 over x. And real quickly, what that does for us is it gets that t out of the denominator. Okay, and then to finish solving for t, you can just square both sides. So t is going to be equal to 1 over x to the second power, which is the same thing as 1 over x squared. All right, and then we're going to take that and plug it in for both of the t's that we see here in y. Okay, so y is equal to 1 over x squared plus 1, all divided by 1 over x squared. Since we have complex fractions, what I'll do is use keep, change, flip. Okay, so I'll keep the top part. I'll go ahead and write in parentheses though. Just looks like that. And then multiply by the reciprocal, which is going to be x squared over 1. Okay, so the 1 on the bottom is not really necessary, but it does help with the first part of the distribution, because this is a reciprocal of that guy. When you multiply them together, you're going to get a 1. So we end up with 1 plus, then this is really just x squared times 1, which will give us that. All right, so what we have here is a quadratic equation that would be symmetric around the y-axis with a y-intercept at 1. It's the parent function just pushed up 1 unit. Okay, so it would start here. It would start at that point, and then it would go over 1, up 1, then go over 1, up 3, then it'd be over 1, up 5, if you happen to remember those patterns. All right, let's go ahead and type in the parametric equations to see if it actually does graph what I believe it will. All right, so I go to y equals, I'm going to type these in. All right, and in addition to that, let me go ahead and set up a window just to make sure that everything's cool here. All right, you're going to notice over here that the t values actually have to be greater than 0, and I'll talk about that in a moment. Okay, but when I graph it, I'm going to go ahead and let this be -10 to 10, because in a way, this part is actually going to take care of itself, and I think that'll actually explain the reasoning behind it a little bit better. All right, for the x's, I actually got it set from 0 to 4, but I'm going to go ahead and leave it as -4 to 3. So as if it's going to graph to that side over there. Okay, actually put that as a 4. For the y values, it is going to be elevated, I believe that. So I can actually start at probably 0. I'll put -1. For the max, let's go ahead and go up to 8. Okay, and this should work. There's our graph. And you actually just see that one side of it there. It seems to disappear right around that area, right? Just sort of blanks out in that spot, and then there's nothing that direction. All right, so that brings us back to this point here, that your t values need to be greater than 0. And the reason for that is because the original parametric equations can't actually have zeros plugged into them or any negatives. This actually says that t has to be positive. You can interpret it that way, that t is only positive numbers. See, if t is 0, you're undefined here, you're also undefined there. So it doesn't work for either of them. In addition to that, negative numbers, a negative would have been fine here, but a negative doesn't work in this case because you would end up with imaginary numbers. Okay, so t needs to only be positive numbers. What that causes to happen is that at the very end of this, which is really going to be right here, you get an open hole. You get an open spot there. Okay, the graphing calculator is going to show you a little bit of gap of space that would be there, but it doesn't really exist. You actually have an open hole, and then you just end up with the right side of the graph like that. So the graph doesn't exist over here, also doesn't exist at that spot. Next, what we're going to do is sort of look backwards from what we did in example 1 and 2. Instead of starting with parametric equations and creating an xy equation, what we're going to do is begin with an xy equation and then break it into parametrics. However, a rectangular equation does not have a unique set of parametric equations. I want to make that point real clear here. A rectangular equation does not have a unique set of parametric equations. So that means that there is not just one answer that would go with a certain situation. For example, this equation we're going to break into parametrics. You have different ways that you can actually set that up, and it will be correct. By varying the definition of the parameter, which I will explain here in just a moment, you can obtain parametric equations that vary in speed and orientation, but not the shape. They'll graph the same picture that you would regardless, but your t's might plot it a little bit faster, is what would happen. And then as far as the orientation, what that would mean is that it might graph in an opposite direction compared to using a different set of parameters. But overall, the picture is going to be identical. For example 3, what we're going to do is model that we can break this equation into parametrics 3 different ways. So what you can see so far on my video is I have an A and I have a B version. There is a C version that we're going to be looking at as well. Okay, we'll go ahead and start with A. Ultimately, what we want to get to is this. You've got an equation for x, you've also got an equation for y, both of which are going to be in terms of t. Okay, one of those in a way is given to you because you're told that t is going to be equal to x. You're told that. So that is the part where we define our parameter, that t is going to be equal to x. Okay, now changing that into x equals is pretty straightforward. You just write it as x equals t and that one's done. To figure out the y equation, what we're going to do is take the definition of the parameter, that would be this t equals, and plug that in to the y equation. Okay, so y is going to be equal, instead of x, you're just going to put in a t, so you get t squared minus 4. And that would be it for the first one. Okay, so if you have a really simple definition of parameter, which is just t equals x, then there really isn't much algebra that you need to do with it. All right, so let's take a look at the other two. We begin with this definition for a parameter, that t is going to be equal to 4x plus 1, and we're going to solve for x. Okay, so we want to get an x equation. We also want to get a y equation over here. All right, so solving for x, we'll subtract 1 from the t. So you got t minus 1. Then divide by the 4, which is going to give you that. And all of that is equal to x. So that'll be your first equation. X is equal to t minus 1 divided by 4. Okay, for the y equation, what we're going to do is go back to our xy equation. Okay, we go back to that equation, and then we're going to substitute in this expression for x. All right, so for the most part, you could just let that be your y equation. But what I'm going to do here is take the opportunity to show you that if we expand this out, we can actually write it in standard form. Okay, so for expansion, what we're going to need to do is square everything that would be here. Okay, for the top part, and I don't got much space here, so let's see if I can actually keep this guy filled in. Okay, for the top, the t minus 1 squared, that will give you t squared minus 2t plus 1. Okay, that would be t minus 1 times t minus 1. It's going to give you that. Over 16 then we have the minus 4. Okay, and if I distribute the 16 to each of the terms, what we'll get is 1/16 t squared minus, this will end up being 1/8, so a negative 1/8. You'll get a negative 1/8 t plus 1/16 minus 4. Okay, and now most of this looks pretty good here, except that you got two constants at the end, so I'll go ahead and just group those together. But for the most part here, this is what I wanted to do with expansion. So I do get 1/16 t squared minus 1/8 t. All right, and then for this part here, 1/16 minus 4, what I'll do is create a common denominator, which would be 16. So this is the same thing as, let's see, 1/16 minus 4 times 16, which is 64/16. Okay, and if I subtract that, I get a negative 63/16. For the most part, this is a good equation that you can use. However, just for the sake of showing some algebra, I went ahead and expanded this out and was able to write it in standard form. All right, for C, we have a different definition for our parameter. T is going to be equal to negative x over 4. Okay, and to solve for x here, so what I'll do is multiply the 4 over. So I get 4t is equal to negative x. And then I'll just multiply or divide by negative 1, which will give me negative 4t is equal to x. Okay, so for your first equation, x is equal to negative 4t. All right, now solving for y, we go back to that original xy equation, and we substitute this expression in for the x. Oops, that'll be a t. All right, and then for the sake of cleaning this up, I'll do a little bit of algebra. I'll go ahead and square this. Okay, so when we square the entire part here, the negative is going to cancel out, which is going to give you a positive. The 4 times 4 will give you 16, and you get t squared. Okay, so not as extensive as the last one, but it is in standard form, just to have it that way. All right, so the interesting thing here is that this set of parametric equations and this set of parametric equations, and even the other one from part A, do graph the same picture. They may have a different speed when they're graphed and a different orientation, but the shape of the graph that you get is going to be identical. So that's what I want to demonstrate next. All right, to demonstrate that all of these are actually the same thing, what I'm going to do is begin by graphing the original equation, which is y equals x squared minus 4. Okay, so I'm going to go to y equals. I have it currently set for just normal functions here. Type in x squared minus 4. And I'm going to go ahead and set up my window to the standard size, which I can do by going to zoom and just hitting 6, zoom standard. So that'll give you like that 10 by 10 screen. Okay, so I'll select that, and that would be our graph. Okay, you have a quadratic. You've got basically the parent function, which would be x squared, except because it was x squared minus 4, the whole thing is moved down 4 units. So that's the picture that we get. Okay, now what I want to do is graph each of these. All right, so I'm going to go back to my settings, go to parametric, select that, and then when I go to y equals, you're going to notice, for the sake of saving time here, I've already typed the equations in. I've got all those typed in. In addition, next to each of these, I've actually turned them off. So if I go to the equal sign and press enter, press enter. All right, you're going to notice that these become highlighted, which means that it'll graph it. So the other two we're not going to see right now. All right, now I do have my window set to that standard size, that 10 by 10. All right, now when I hit graph, unfortunately, you might not see the whole picture. You actually just get the right side of it. Okay, and that does not come down to the fact that our t values have been limited or anything like that. What that is that when I go back to the window, because I had it set to a standard, it automatically defaulted with the t values from 0 to 2 pi. Okay, but we don't really have a limitation. So what I'm going to do is more or less guess on a good set of values for t. So I'm going to try, let's see, negative 10 to 10. So you can't actually type in negative infinity to infinity, but you can start with a range of values, and if it does not graph the whole thing, then you can just extend that range. Okay, so let's see what this one does then. We get the whole picture. So at least for that set it works. And now notice this picture is x squared minus 4, the same one I showed, except I'm graphing it using the parametrics. All right, let's go back to the parametrics. And go ahead and turn on the second one. Just press enter there and you'll highlight it. And it should graph the same picture. You should actually see the blue get covered up in red. All right, you're gonna notice it didn't cover all of it. That is probably gonna come back to my t values not being big enough. Let's try negative 50 to 50. So there's the blue. Looks like we got enough for the red one show. But the most important thing is that you notice it is the exact same graph. All right, let's check out the last one. And I think this one actually is going to graph faster. It's a less complicated one here, so let's see the red line become black. There it is. All right, so given an equation that would be y equals x squared minus 4, you can break it into different sets of parametric equations. It just depends on how we define that parameter, but you can create tons of different sets that would go with it.
Later, blah.